Imagine being told that for over a century, humanity has been building one of the most inefficient machines ever created, and then being told we had already perfected it, that no matter how much money we spent, no matter how advanced our simulations became, we would never push a gasoline engine beyond a certain limit. 41%. That was the number, a hard ceiling, a boundary defined not by companies, but by physics itself. And for years, the entire automotive industry accepted it. But what if that limit was never real? What if the world's most advanced engineers didn't hit the limits of thermodynamics, but the limits of their own imagination? Because in 2026, that ceiling didn't move. It shattered, and what replaced it may change the future of the automobile entirely. To understand why 48.41% thermal efficiency is so disruptive, it's necessary to step back and look at how the industry got here. Because the internal combustion engine was never designed to be efficient, it was designed to be practical. In its earliest form, the gasoline engine was brutally simple: fuel, air, spark, explosion, motion. But beneath that simplicity was a fundamental problem. Most of the energy released during combustion never reaches the wheels. Instead, it escapes through heat, through exhaust, through friction. For over a century, engineers have been fighting this invisible enemy, trying to capture more of that lost energy, and slowly, they made progress. From early carburetors to direct injection, from fixed valve timing to variable valve control, from the Otto cycle to more advanced thermodynamic strategies like the Atkinson cycle. Each step was an attempt to bend physics without breaking the engine. Then came hybridization, and this is where things began to change. Because companies like Toyota realized something critical. The engine didn't need to be powerful all the time. It needed to be efficient most of the time. With systems like the Prius, and later the dynamic force engines, Toyota pushed thermal efficiency to 41%. An extraordinary achievement, and requiring billions in research, precision manufacturing, and deep optimization of combustion timing, airflow, and expansion ratios. And when they reached that number, the industry reacted, not with urgency, but with acceptance. 41% became more than a milestone. It became a psychological boundary, because pushing beyond it meant extreme trade-offs. Higher compression ratios increased the risk of engine knock. Hotter combustion threatened material limits. Colder exhaust reduced emissions system efficiency. Every gain became exponentially harder and more expensive. So gradually, the industry shifted its focus from improving combustion engines to replacing them entirely. Electric vehicles became the new frontier, the new narrative, the new future, and for a moment, it seemed inevitable that the internal combustion engine, after more than 100 years of evolution, had reached the end of its story. But while Western and Japanese automakers were preparing for an electric future, something very different was happening elsewhere. Because some engineers looked at the same problem and came to a completely different conclusion. They didn't see a dead technology. They saw an unfinished one. The physics problem no one could escape. At its core, the internal combustion engine is not a mechanical system. It is a thermal system, which means it is governed by thermodynamics. And thermodynamics is unforgiving. When fuel burns inside an engine, it releases energy in the form of heat. That heat expands gases, pushing the piston down, creating motion. Simple in theory, but in reality, most of that energy is lost before it can do any useful work. A typical gasoline engine wastes nearly 70% of its energy. Some of it escapes through the exhaust hot gases, leaving the system before their energy is fully extracted. And some of it is absorbed into the engine block, heating up metal instead of moving the vehicle. And the rest is lost to friction metal surfaces sliding against each other thousands of times per minute. This is not a flaw in engineering. It is a consequence of physics. Because heat engines are bound by temperature differences. The greater the difference between combustion temperature and exhaust temperature, the more efficient the system can be, but increasing that difference comes at a cost. Higher combustion temperatures risk damaging materials. Lower exhaust temperatures interfere with emission systems. So engineers operate within a narrow window, pushing against limits without crossing them. For decades, this balance defined what was possible, and it is why 40% efficiency was once considered extraordinary. The RPM problem. The industry ignored. But physics was only part of the problem. The bigger issue was how the engine was being used. In a traditional vehicle, the engine must operate across a wide range of conditions. Idle in traffic, accelerate on demand, cruise at high speeds, climb hills, handle sudden loads, which means it constantly changes speed from low RPM to high RPM, rarely staying in one optimal range. And that is where efficiency collapses. Because every engine has a sweet spot, a narrow band where fuel combustion, airflow, and mechanical motion are perfectly balanced. Outside of that range, efficiency drops dramatically. Yet traditional cars force engines to operate outside that optimal zone most of the time. To compensate, engineers introduced transmissions, gearboxes designed to keep the engine within a usable range. From simple manual systems to complex multi-speed automatics, to planetary gear systems like Toyota's ECVT, each one attempting to solve the same problem, matching engine behavior to real-world driving conditions. But these solutions introduced new inefficiencies: weight, mechanical friction, the energy losses during gear shifts, hydraulic systems consuming power. The gearbox became a necessary compromise, a mechanical patch for a deeper architectural flaw. Why traditional solutions failed? So the industry kept optimizing. Better gear ratios, more gears, smarter control systems, hybrid assistance. But every improvement followed the same logic. Adapt the engine to the car. Instead of asking a more radical question, what if the engine didn't need to adapt at all? Because as long as the engine is directly connected to the wheels, it is forced to respond to every change in driving conditions. And that means it can never operate at peak efficiency consistently. And this is the contradiction at the heart of modern automotive engineering. The engine is most efficient when it is stable, but driving is inherently unstable. Acceleration, braking, traffic, terrain, constant variation. So the system is fundamentally misaligned, and no amount of incremental optimization can fully resolve that mismatch. This is where the traditional approach reaches its limit, not because engineers lacked skill, but because they were solving the wrong problem. They were trying to make the engine more flexible, when the real solution was to remove the need for flexibility entirely. And this is the point, where a different kind of architecture begins to emerge. A one that doesn't try to optimize the old system, but replaces the logic behind it. Power electronics, inverters, thermal management, all into a single compact unit. Instead of shifting gears, it routes energy, directly, electronically, instantly. For most driving conditions, the engine never physically connects to the wheels. It operates purely as a generator, while the electric motor delivers smooth, continuous torque. Only at high speeds where electric motors become less efficient does the system directly couple the engine to the drivetrain. And even then, only under optimal conditions. The car becomes a system, not a machine. Managing this level of complexity requires more than mechanical engineering. It requires computation, real-time decision-making, and energy flow optimization. Modern hybrid systems now rely on advanced processors, analyzing driving conditions dozens of times per second, predicting terrain, anticipating load, balancing battery usage with fuel consumption. This is no longer a car in the traditional sense. It is an intelligent energy system, a rolling power network constantly deciding the most efficient way to move forward. And this is how 48.41% becomes possible, not through one breakthrough, but through the integration of many: architecture, combustion, thermal management, and computation, all working together as a single system. To understand how disruptive this system truly is, it must be viewed not in isolation, but in comparison. Because for decades, companies like Toyota built what many considered the most efficient hybrid systems ever created. The ECVT, a planetary gear set capable of blending engine power with electric motors seamlessly. No gear shifts, no interruptions, just smooth, controlled energy distribution. It was brilliant, but it was still mechanical, still bound by physical components, still carrying internal losses, still forcing the engine to participate in the act of driving. And that is the limitation. Because no matter how refined the system becomes, as long as the engine is tied to the wheels, it can never be perfectly optimized. In contrast, the newer architectures emerging from China remove that dependency entirely. The engine is no longer part of the drivetrain. It becomes a dedicated energy unit, operating in isolation, running at peak efficiency continuously. And this is where the gap begins to widen. But perhaps the most interesting comparison is not with other hybrids. It is with electric vehicles, because for the past decade, EVs have been positioned as the inevitable future: zero emissions, high efficiency, minimal mechanical complexity. But this future comes at a cost: large battery packs, expensive materials, significant weight, and a dependency on charging infrastructure that is still evolving. In many ways, electric vehicles solve the problem of combustion by removing it entirely, but these new hybrid systems solve the problem differently. They don't eliminate the engine, they perfect its role. By combining electric driving for daily efficiency with ultra-optimized combustion for long-distance travel, they create a system that challenges both categories. Not fully electric, not traditionally hybrid, but something in between, that may be more aligned with real-world usage. And this is where the industry tension becomes unavoidable. Because while Western automakers committed billions to an all-electric future, Chinese manufacturers focused on the transition itself. They optimized the bridge instead of jumping directly to the destination. And now that strategy is beginning to show its strength. Because it is not just about technology, it is about economics. Smaller batteries reduce cost, higher efficiency reduces fuel consumption, simpler systems improve scalability. And suddenly, a new question emerges, not about what technology is possible, but about what technology makes the most sense. Because if a vehicle can deliver electric-like driving experience with significantly lower cost and dramatically extended range, then the definition of future mobility becomes less certain, and in that uncertainty, a new competitive landscape is forming. For more than a century, the internal combustion engine has been defined by its limitations: inefficiency, heat loss, mechanical complexity. And for years, it seemed like those limitations had finally caught up with it, that its role in the future of mobility was coming to an end. But what this new generation of engineering reveals is something far more interesting. The engine didn't reach its limit. It was redesigned, not as the heart of the car, but as part of a larger system. A system where energy is no longer controlled mechanically, but intelligently. And in that transformation, something unexpected happened. An old technology became new again. So the question is no longer whether the internal combustion engine will survive, but in what form. Because the future of the automobile may not belong to a single technology, but to the systems that integrate them best. And this may only be the beginning.